Okay, so welcome to this MA 161 exam one from looks like it's spring 2022. Um, I believe this is the earliest exam that I am going to be doing for this entire class. So this is most likely your first boiler exams video, at least for this class, or maybe in general, because this is only Calc 1. I don't think we do anything earlier than that. So if you're new around here, welcome to the show. I hope these videos will be informative and helpful for your studying needs for the exams. So we can go ahead and get started on the first question here. The domain of f of x equals this is what? So what is the domain of the function that it gives us? So, okay, quick, what are domains? So basically, domains are just the values for x that you can plug in and it won't mess up the function or make it undefined or divide by zero or anything super weird like that. So, um, a good example of this is what I just said, is if you divide by zero. So say we have, I'm going to make a different like example function here. Let's define it as just 2 over x. It could be whatever. So you'll see here, x can be, you can plug in basically anything for x. You can do -1, you could do +1, you could do 1,001. But what happens if you try to plug in 0? Well, then this becomes 2 over 0, and this is, you can never divide by 0. You can never do that. So in this case, the domain of g of x goes all the way from -infinity to 0, skips over it, and then goes all the way to positive infinity. Basically, this notation just means include all the numbers, from -infinity to positive infinity, but just skip over 0. Because if you try to plug in 0 for x here, you'll divide by 0, and we can't have that happen. So that's basically what domains are, just what you can plug into functions, and it'll actually spit out like a valid, real answer. So there's a couple of ways that can happen where when you plug in a number for x and it'll be not good, it'll be undefined. The first one I just said is if you try to divide by 0, then x cannot equal 0. A second one that you probably heard before is when you take a square root of x. Whatever's inside, you can't take the square root of a negative number or else you get an imaginary number. And we're not doing that this early on in calculus. So for this case, when you have a square root of x, x must be greater than or equal to 0. I note that I put greater than or equals to because you can take the square root of 0, so we need the equals part of that sign there. And then a last one, which is a little more obscure, but you will definitely encounter it at some different points, is when you have logarithms. So whenever you take the logarithm of x, x must be positive. It can't be negative and it can't even be 0. You can't take the logarithm of 0 or a negative number, so x must be greater than 0. So those are the main three sort of restrictions on our domain that we'll encounter throughout these domain problems. So now how we figure out, like how do we take this and figure out what the restrictions are, we basically just, see which one of these appear in this, and then we will basically just, set it not equal to 0 or greater than or equal to 0, things like that, and then basically just solve for x. So let me show you what that means with the first part of this. So looks like we kind of have three different restrictions that we'll have to worry about. We've got this square root, we've got this square root, and we have this fraction. So we've got two square roots, and we've got one fraction. So those are the three restrictions on our domain. And usually you'll have three, sometimes you'll have two if it's a more complicated problem. So let's go ahead and start with the first one, square root of x minus 2. How we'd solve this is we rewrite that, so square root of x minus 2, and then what did we say earlier? X must be greater than or equal to 0. So whatever's on the inside, actually I messed that up. Whatever's on the inside here, which is the inside of the square root, whatever's inside must be greater than or equal to 0. And then what we do here is we just solve for x. So we do plus 2 on both sides, so x is greater than or equal to positive 2. So there we go. We have our first restriction now. I'm going to write it up at the top left to keep track of everything. I'm eventually going to have 3 of them here. So, all right, now we're done with the first one. What about the second one? Let's do the other square root one. So remember, anything that's inside the square root must be greater than or equal to 0. So 3 minus x must be greater than or equal to 0. Now we just, looks like you can subtract 3 from both sides. So negative x is greater than or equal to negative 3. And then multiply both sides by a negative number. Get x is, okay. This is important. So this might happen sometimes in your domain problems as it just did here. So um, notice how with all of these inequalities, we have, obviously, inequality signs. So whenever you have inequality signs like a less than or a greater than, and you multiply or divide by a negative number, as we just did here, we basically multiplied both sides by -1, you must flip the sign. So this is a greater than or equal to sign. Since we just multiplied by -1, we have to make that a less than or equal to sign. So x is less than or equal to positive 3. So there you go. That might happen sometimes. All right, so now we have our second restriction. X must be less than or equal to 3. Put that up here, x less than or equal to 3. And now we can find our third one, which we said was this fraction here. So whatever is on the bottom cannot equal 0. So square root of 3 minus x, so that's, again, that's the denominator. That's whatever's on the bottom. It must not be equal to 0. So now we're here. How can we solve for x? Well, we can, let's see, we can square both sides to get rid of the square root. So this is now 3 minus x. It cannot be equal to still 0. 0 times 0 is just still 0. And then that's kind of the same thing we did here. We just got to subtract 3 from both sides and then multiply by -1. So negative x is not equal to -3. And then x is not equal to positive 3. So okay, so now we're here. And since, okay, we didn't have to do that, times -1 thing or flip the signs because there is no sign to flip. It's just a not equal sign. So you don't really need to flip it, I guess, because it can't be flipped. All right, so we have our third one now. X must not be equal to 3. And now we have all 3 of our restrictions on our domain. We just need to put it in a form that it likes, the proper domain notation form, whatever you call it. So how do we interpret this? So basically, so what each of these means, if we see a bracket here, it means it does include the 2. So basically, if x equals 2 in the function, what a is saying is that it's okay. Yes, you can plug in 2 for it, but you cannot plug in 3 because 3 has a parentheses right next to it. And something like, let's say, B right here, it's saying you can't plug in 2 for x and you can't plug in 3 for x because both 2 and 3 are surrounded by parentheses. For something like E, it's saying yes, you can do 2 and 3 because it's brackets. So, well, let's see what we have over on the top left again. So x must be greater than or equal to 2. So it's saying, okay, yes, 2 is okay. You can plug in 2 for x because we have this greater than or equals sign here. So it looks like it's going to be a bracket around the 2, and it's, on the left side because A, 2 is less than 3, and B, it's saying x must be greater than 2. So x must be going, greater than. And then comma, since all these look like they're going to be like a 2 comma 3 or 2 comma infinity thing here, so we can just do 2 comma 3, assume it's a 3. Let's see, we've got x must be less than or equal to 3. So this is saying, yeah, you can also plug in 3 for x because it's a less than or equal sign here. So it should be a bracket, but wait, we've got this third restriction down here. X cannot be equal to 3. So this really should be a parentheses because x cannot equal 3. And with that, looks like our problem is all done. It looks like it's A, 2 inclusive to 3, I guess, exclusive. So that's the mathematician's way of saying that. So that's how you'd find a domain of a function. This is a very common first problem on these exam ones. So this is really, you really should have these locked down and figure out how these domains work. It'll be basically on every exam one. So again, just remember these three kind of types of restrictions that can impose. No, the three types of, yeah, the three types of restrictions that can make restrictions on your domain. It'll be, 1 over x, square root of x, and a logarithm of x. And then know that whatever's, on the inside, the x, you just set that, not equal to 0 or less than or equal to 0 or greater than or equal to 0. And then basically just solve it. You'll get your two or three restrictions, and then you just put it in the form that it wants. So these domain problems, once you break it up like that, they are not so bad. So how'd you like that? Your first boiler exams question, 100% complete. How do you feel? All right, question two. This is another common type of exam one problem, transformations. So basically, it's going to give you the function of a graph, which this is not what that looks like. It's just an example graph that I've drawn there. It's going to want you to uh, transform it. It's going to want you to shift it like left, right, up or down, however many units, or maybe it wants you to like squish it so it's like shorter and tinier, or maybe stretch it so it's taller or maybe wider. Or a rare case that I don't think I've actually seen yet is it wants you to flip it, like mirror it along either the X or the Y axis. So those are a couple different transformations that it'll ask of you. This one looks simpler at first because it's just one transformation. Usually these problems are like two or three transformations that you compile into a big function. But this one is just one to start. It's just 3 units to the right. So uh, basics. Sorry, I shouldn't say basics because this is might be your first time doing this. But um, okay, just simple translations and shifting things left, right, up, or down. So let's rewrite the top function. I'm going to rewrite it a little differently so it's clear what's going on. It's e to the power of negative x. I'm going to leave some room here for something that I'll explain right now. So there's 4 cardinal directions that you can shift something in, up, down, left, or right. When you are doing something horizontally, like so we're doing a 3, we want it to be moving 3, we are doing something horizontally. We're moving something to the right. So since it's horizontal, we're going to put that 3 next to the x. We're going to put the x there. It's either going to be plus or minus 3. We'll figure that out in just a second. If it was a vertical action, if we wanted to move it up 3 units or down 3 units, we would put the 3 on the outside here. And that's the reason why I left this space here and also do these parentheses, because if I were to just drop those, like negative x, and then let's say I wanted to do a plus 3, that is technically a different problem because if I were to keep these parentheses here, it would be clear that it is a plus 3, but if we were to drop these parentheses, we would have to basically FOIL this minus. This plus would become a minus, and that's a different problem. We get the wrong answer. So parentheses here, we have a 3 there, and now is it a plus or is it a minus? So this is the interesting part. You'd think that it would be a plus, right? Because we're going to the right. Usually right is associated with like positivity. Like as you travel right on the number line, numbers get bigger and bigger and bigger, and they're positive. So a plus. Uh, but it's actually different. It's the opposite of what you'd think for horizontal. We're going to put a minus here. Uh, I think I know why, but it'd probably take a little too long to explain that, so I'm not going to do it here. But yeah, just remember that when you're doing horizontal actions, you're going to do a minus instead of a plus for right. And conversely, if you want to make something move left a given number of units, you'd put a plus. So there we go. Now we have our completed function. Usually you'd be done at this point, but since this was just one transformation, it looks like it wants us to fill in all that extra work that it'd make us do with like 2 or 3 transformations with this. It wants us to put it in a different form, wants us to simplify it. So Let's see, what would we do here? Well, first off, we can do what I talked about earlier. We can FOIL this minus sign. So this would become e to the negative x plus 3. And now, okay, it looks like, let's see, a lot of these involve, actually not a lot of these, just this one actually. It involves two uh, e to the power ofs. So remember that whenever you have like a to the power of something times a to the power of something else, that just equals one exponent with those two, or one base with those two exponents being added together. So a to the power of b times a to the power of c equals a to the power of b plus c. So we can basically take that and apply it with what we have here. This just, in reverse. This looks like it would become e to the power of negative x times e to the 3, e cubed. So C is our answer here. Um, yeah, transformations problem. I wish this would be a better, like I'm thinking this is a lot of your guys' first exam on this site, so I wish this was a better introductory transformations problem where it had like maybe it had like two translations and then a I forget what, like a scalar where it's scaled down on one of the axes, it's like squished or something, but one of these transformation problems, it's still a pretty good starting point. So just remember basically the horizontal, rule. When you're doing horizontal, you flip the sign and it's affected on the x instead of on the outside. And then those last 2 points are opposite for when you're doing a vertical action. And then sometimes it'll have you simplify the answer. Okay, number 3. This is an inverses problem. So we're usually in these inverse problems, you're given a function, f of x, and then you are asked to find its inverse, and then sometimes you have to plug in a value for x into its inverse. So the setup for these problems is not too bad. It's just a lot of work that you have to do afterwards. So how to do inverses? Uh, Replace the f of x with a y, so like y equals instead of f of x equals. Then just rewrite everything else. 2 plus 11x, all that is square root. Uh, cool. Now we have that rewritten with the y instead. And now what we're going to do is we're going to replace the y's with x's, and we're going to place the x's with y's. So now we're in this state, and now what we do is we just solve for y. So we do a bunch of, adding, subtracting, multiply, dividing to get this back in a state where it's y equals. And then whatever is left here, that will be the inverse. So that will be the inverse of f. So that's how we find inverses. So now we can just go ahead and actually do this and figure out what y equals here. So let's see, first step, we should probably subtract 2 from both sides, get rid of that. So this becomes x minus 2 equals the square root 2 plus 11y. Now we can square both sides to get rid of the square root on the right side. So this becomes x minus 2 squared equals 2 plus 11y. Should I go ahead and, I probably should go ahead and expand. No, actually, I'm going to say we shouldn't expand this because, I mean, if you want to, you can. It's just, I think it would end up being more work for you. And I think we can just leave it as that, and we wouldn't really have to do anything else because we're just going to plug in 5 into it at the end. So I think it'd be easier if we left that unsimplified. So now we can subtract 2 again, get rid of that 2. So this becomes, sorry, excuse me, I had a heart palpitation. That was weird. X minus 2 squared minus 2 equals 11y. Now we can divide by 11 on both sides to get y by itself again. So this is going to be y equals x minus 2 squared minus 2 all over 11. So, all right, looks like we're on the right track because we have this divide by 11 right at the end, and all of these answer choices involve 11 in the denominator. So we're probably on the right track here. So, all right, so now that we've got y all by itself, we now have our inverse. So this is the inverse, or actually, usually professors will call it f inverse of x. So we have f inverse of x, and now it just wants us to plug in 5 4x here, and then we'll get our answer. So I'm going to partition all that off and rewrite it up here, but with 5 instead of x. So 5 minus 2 squared minus 2 all over 11. 5 minus 2 is 3 squared minus 2 all over 11. That is a 111. 3 squared is 9. 9 minus 2 is 7 over 11. 711. That is a great store. Um, yeah, so inverses. This was a great introductory inverse problem. It was not super crazy, but it also had all of the hallmarks of an inverse problem. So remember that you just basically flip the positions of the x's and the y's, and then solve for y, and then whatever you have remaining is the inverse. And then you can go ahead and plug in values from there. All right, number 4, express the given quantity as a single logarithm. So how are we going to do this? Because there's 3 different logarithms that I guess it wants us to like compress down. So we're going to use a couple different properties of logarithms that you can use to combine these into just one. So the first one that is probably going to do it at the start is if you have, let's see, how can I write this? Oh yeah, okay, before I actually get into what I was about to say, is you might see logarithm and be like, oh, wait, there's no logs here, there's just these ln's here. So in case you're unaware, in case you don't know, which is totally fine because we learn everything for the first time at some point in our lives, ln is just log base e. So whenever you have ln of something, that's the same as log base e of that something. So that's just what that means. It'll come up a lot because log base e is really useful in mathematics. So you'll usually just see a lot of ln's instead. Um, Anyways, so what I was getting to is those properties of logarithms that you can use to condense things. First one that I think we'll have to do is if you have something on the outside, let's see, c times log of x. This is the same as log of x, but that c has been raised to the exponent of x. So now it's like in there and it's x to the power of c. So it looks like we'll do that a couple of times. We'll probably have to do it here, move it out there, and again right here, move it to the exponent there. And that'll make it easier to condense this whole thing because we won't have constants at the front of everything, it might jam some things up. So yeah, and then it looks like another one that it wants us to use, another property of logarithms, is if you have 2 logarithms that are being subtracted, so like log of a minus log of b, this is the same as, I hate this circle thing. I've got these buttons on the side of my stylus that I should probably deprogram, I guess. If you have log a minus log b, this is the same as one logarithm where they are being divided on the inside. So a over b. So we'll also be doing that because we've got a minus log and a minus log there. So, all right, now that we have those two, I think that's the only 2 that we need. So we can go ahead and tackle this problem. First up is what I said first. So when you have the constants out on the front of the logarithm, you can make them exponents. So we can move this 2/5 out to the exponent. This will become ln of x plus 7 to the power of 2/5. Now, instead of leaving it as 2/5, I'm going to simplify this as x plus 7 squared to the 5th root. So the 5th root of x plus 7 squared. This 2 is the numerator and this 5 is the denominator if you ever want to like extrapolate it, do other, fractional exponent things with it. So we have that. That's the first term. Second term doesn't have a constant, so we'll just rewrite it. ln of the 5th root of x. By the way, you can go vice versa. So since this is the 5th root of x, we can rewrite this as x to the 1/5 power if we wanted. But we're not going to do that. We're going to keep it as the 5th root. And then minus the third term. So we've got another one of those constants out front. We're going to move it out to the right. We're going to make it an exponent. So this is now ln of x squared minus 8 to the 1/5 power. Again, I'm going to rewrite this as a root instead of just a fractional exponent. So this 1/5 power just becomes fifth root. So since the numerator was just 1, that's the same as raising all of this to the first power. That doesn't do anything. So I'm going to keep it as is. All right, so now we're in this state. We've got no constants out in the front of any of these terms. So now we can go ahead and do the second one that I told you about. So when you have two logs being subtracted, you can combine them into one log where they're divided. So PEMDAS wants us to go from right to left, so we'll do the first two terms first. ln of that minus ln of that. This is just putting them on the top and bottom of one another. So this is ln of, the top is the fifth root of x plus 7 squared. The bottom is the fifth root of x. And there we go. We've combined those two terms. What we can do even further is that since both the top and the bottom have a fifth root in them, that's the outside part, the fifth root, we can just combine it into one fifth root. So this will all become the fifth root of the fraction. So that makes it even simpler. And now we've got that third term to worry about, ln of fifth root of x squared minus 8. I guess technically now it's the second term. We can do the same thing again where we divide it all into one logarithm. So this is now ln of the fifth root of x plus 7 squared over x divided by the fifth root of x squared minus 8. So there we go. We now have our one logarithm, but we have to do a little more simplifying before we do that. First thing we should probably do is, again, we've got two fifth roots on the outside, so we can combine them into one fifth root of absolutely everything. And now, okay, we just have two fractions that we should probably just put into one fraction with one numerator and one denominator. Hold on, I have an answer key here. Which one did it say was correct? I should have memorized this ahead of time. 4 is E. Okay. E is that. So, okay, so we've got our two denominators here. So those are both the denominators of one fraction. So this is now, looks like it would be ln of the fifth root of x plus 7, which is the sole numerator right up here, and then our two denominators, which are x and x squared minus 8. And that is the answer. That's how you get the answer. So, okay, properties of logarithms. Yeah, there's really just those two, where if you have constants outside on the front, you can raise it to the top, x to the power, the exponent, and when you have these minuses, you can combine multiple logs that are being added or subtracted into just one log. So those two properties can be used in a lot of these different calculus topics, usually derivatives. So I guess that's why they're priming you on these now. So they're good to know. And also these are, I think they've been on every single one of these exam ones that I've had so far. So this is prime real estate for what'll probably be on your exam one. So yeah, just these condensing problems are basically all you'll really come across on these though. So there you go. Okay, question 5. Okay, this is a little weird because it's oddly simple. It's just the wording is a little weird. So it gives you a function in f of x, and it wants you to find and simplify the difference quotient. This is the difference quotient. All it wants you is just for these two f's, these two functions here, substitute in the function that it gives you, and then simplify it all down, and it'll end up looking like one of these. So kind of weird how it says like difference quotient or whatever, but it's not so bad. So all we do is just plug in 2 plus h for x and then 2 for x, and then put them all up there, and we're golden. So okay, so on the top we have f of 2 plus h. So this is 3 minus 2 plus h squared minus 2 plus h minus f of 2. So this is now 3 minus 2 squared minus 2 all over h. So this is the point where I'm going to say I'm going to exclude this divide by h for now because we're going to have to write that every single step of the way, all the way to the bottom. That'll get a little messy. So I'm going to keep it just as the numerator for now, and then we'll just remember to divide by h at the very end. So simplifying this now, let's see, we can do 3 minus, okay, when we FOIL this out, when we FOIL the 2 plus h squared out, we get 4 plus 2, wait, that's, how does this go again? It's 2 plus, no, 4h, sorry, I don't know what the hell I'm thinking. This is algebra stuff, plus h squared, and then minus, whoops, minus 2 minus h. So this minus gets distributed to both of those. And since they're both positive, they both get changed to minuses. So we have that now. We can really just drop the parentheses. Now we've got minus 3. So we're distributing all this now. So this is minus 3 plus 2 squared, which is 4, and then plus 2. And now we can simplify everything. So we've got an h squared all the way at the front. How many h terms we have? We have one here and we have one here. So 4h minus h is 3h. And then we have a bunch of just constants. So 3 minus 4 is negative 1. Minus 2 is negative 3. Minus 3 is negative 6. Plus 4 is negative 2. Plus 2 is 0. Wow, all of these constants just happen to collapse down to 0. That is probably intended because remember, we still have to divide everything by h. So look at this. All of these terms have an h in it, so we can cancel out an h from everything. So this becomes now h plus 3, and we have, oh, I thought we had our answer. Did I do something wrong? Is this h supposed to be a plus here? Minus 2 minus h. Oh, I did do something wrong. So, okay, let's fix this now, because we all do mistakes, and we just fix them and keep plugging away. So, I think it's because this minus, or this term out here was being minused here, so being subtracted. So, I think what we do is we do all this in a parentheses and then distribute that minus out afterwards. So, this is still the same thing. It's 4 plus 4h minus no, plus h squared, but now all of these are going to be flipped. So this is minus 4 minus 4h minus h squared. Okay, I think that's what the problem was. So we're here now. We have a minus h squared at the front. Minus 4h minus h is minus 5h. That's those two terms. And then hopefully all of these constants still check out. So 3 minus 4 is negative 1. Negative 1 minus 2 is negative 3. Minus 3 is negative 6. Plus 4 is negative 2. And plus 2 is 0. So this is still just plus 0 here, which is good because we divide everything by h. Everything's got an h in it, so we can cancel it out. This becomes negative h minus 5. There we go. That's our answer. Okay, this is a great problem for two reasons. One, because this is a great difference quotient problem. I think I've done like 2 of these before, so it might be on your exam. And 2, because I showed you that after 4 math classes, I'm still doing these dumb mistakes. So if you do something like that in an exam, it is not a you problem. Everybody does those dumb algebra hiccups every once in a while. So don't worry if you do them. Just hopefully you'll catch it and like you'll get a wrong answer at the end, and you can go back and figure out what you did. So we all can recover, I guess, is the motto of this question. Okay, question 6. All right, this is okay, we get to do derivative here. This might be your first derivative on these problems. So the altitude of a drone t seconds after it takes off is given by this function. I guess they used h instead of, f, like f of t, because it's like the height, stands for height. What is the drone's average velocity over the time interval from, I guess, launch, 0 seconds after takeoff, to 3 seconds after takeoff? So in those first 3 seconds, what's the drone's average speed? Okay, so Well, first thing I think we should do is, since we're asked to find the average velocity, we should probably find the velocity function. If we were to find this velocity function, we could plug in values into it, and then we could get our velocity at different points of the drone's launch. So what we have now is the position function, where if we plug in, let's say 5 for t, our resulting value will be the position of the drone after 5 seconds. If we were to find our velocity function, we could find the velocity of the drone after 5 seconds, or 3 seconds, or 0 seconds, or 10 million seconds, who cares? So this is where our derivatives come into play, because the velocity function is just the derivative of the position function. So to find this derivative, let's rewrite the original function, 1/6 t cubed plus 4, and then we do our derivative. So I think the first derivative rule that they teach you guys is the exponent rule. So this is the case where if you have an exponent acting upon the variable, what you do to derive it is you move it out to the front and then reduce it by 1. So let's do this now. Taking the 3 out to the front, we get 3 times 1/6, and this is now times t squared. So 3 minus 1, we drop it by 1. 3 minus 1 is 2. So simplifying this now, we get 3 times a 6 is just 1/2 t squared. Okay, now what the heck do we do with this plus 4? So imagine if this plus 4 had a t to the 0th after it. That's really the same thing, because t to the 0th is just 1 every single time. So it doesn't change it at all. So what happens if we do that exponent trick? Well, this 0 gets put out front. So this is now plus 0 times 4 times t to the, well, it could be anything. It would be -1, but we've got this 0 here, and that 0 is going to make that entire term 0. So we really just ignore it. So this is another common thing you'll have to remember in derivatives. The derivative of constants, aka just numbers with no x or t or y or anything in it, are 0. Derivatives of constants are just 0. So this down here, this is our completed derivative, and this is our velocity function. So now that we have our velocity function, well, first let's realize what we've just done. This is now, if we were to plug in like 5 for t, our resulting value will be the velocity of the drone after 5 seconds. So that's what this means. Now to find our average velocity, what we can do is just imagine, let's see, let's put it up here. We've got a graph, and we've got, let's see, that's the drone's velocity at that point, and this is the drone's velocity at that point. So let's say it goes like that or something. That's a bad drawing. Let's do something like this. Say it's like really picking up speed. So if we have something like this, in order to find its average velocity, we can really just draw a straight line in between them and then take like the slope of the line, and that'll be the average velocity. So what we can do to find that is take the velocity at the first value minus the velocity at the final value all over the length of time, aka the first value minus the second value. Or actually, it'd probably be switched around. It'd be 3 minus 0, but let's keep it consistent like that. So now we can just use this, and we can use this, and we can find our average velocity. So v of 0, this is just 0, because if we were to plug in 0 for t, that's just 0 squared, and then 0 times a half. So that's still just 0. Minus v of 3. So if we were to plug in 3 here, this is 1/2 3 squared. 3 squared is 9. 9 times a half is 9 halves. So it's 0 minus 9 halves. This is just negative 9 halves. All over 0 minus 3, which is negative 3. Negative 9 halves divided by negative 3. This is the same as negative 9 halves times 1 over negative 3. This equals, let's see here, this equals 3 halves. There we go. B. So the average velocity of the drone between the between 0 seconds after takeoff and 3 seconds after takeoff is 3/2 feet per second. I believe that's what it's saying. Okay, that was, I'm running out of breath here because this is my sixth problem and I'm running out of stamina, but um, yeah, average velocity problems, this is a pretty standard one. So what you'll need to remember is how to do basic derivatives, the exponent rule and what to do when you have constants. And then you also remember how to find, that slope here, which is just, you might remember this from like algebra when you've taken that. This is just the, um, I believe it's how you find slope if you know 2 points. That's how you can find like the slope of a line between 2 points. So that's what we used there. Just kind of adapted it to our situation and, just plugging in values from there. And with that, you're half done with this whole exam. Wow, that was, I think I'm still on time. I think I'm still under 30 minutes at this point. But you can see how if you're not fully grasping these concepts, you can definitely run over that 1 hour limit that I think they give you, unless they've changed it. So, um, yeah, this is why we're making these videos for you guys. You can get really fast and good at doing all these problems. So hopefully they've been working for you so far. Okay, question 7 now. What is the range of this function? So, all right, remembering what a range is now. So domain and range are kind of the opposite. So if domain is the values that you can plug into x, then the range is the values that I guess you can expect of y, of, this. So let's see an example here. Looks like this is a sine function. So let's just imagine a simpler case where you have g of x equals sine of x. No like squared or negative or anything. You know that sine is just kind of a wavy, it's a sine wave. That's what they are. And then this is the big axis. You know that it peaks at 1 and uh, the valley is at -1. So we'd say the range here is from -1 to +1. So that's what we would say the range is. The domain is, negative infinity to positive infinity because it goes all the way to infinity on both sides. But the range is more restricted because sine waves only stay bounded between -1 and 1 inclusive. So that's what range is. And now to actually figure out this problem, I think there's a mathematical way you can go about doing these. But since this is it's a little bit easier since it's just a couple modifications of a vanilla sine wave. I think we could just figure this out like graphically and verbally and find our answer. So not really sure why I erased all of that, but let's do it again. Our sine wave here. Remember it peaks at 1 and or peaks at +1 and its lowest point is at -1. So we'll start with that, -1 to +1. And now what is the other transformations doing? So it looks like it's being squared, right? So it's being squared and then it's being, taking the negative of being multiplied by -1. So first off, what does squaring do when you square some value? Uh, it makes it positive, right? If you square a negative number, it makes it positive. So we know we can't have any values that are negative right now. So this range, it must be from 0 to 1 at this point. And it can't be anything greater than 1 because we know all of our values, they must be less than 1. That's what this says here. They must peak at 1. And the only way for a value to grow in size after being squared is if it's greater than 1. So that's why we can't have any values greater than 1 after the squaring. So we know that our range now is from 0 to 1. Also, we also know that this should remain a bracket. It should still remain 0 inclusive because you can plug in zeros at each of these points. These are all when you'd plug in 0 and you'd get 0. No, sorry, not when you plug in 0. You can plug in uh, I believe pi, 2 pi, 3 pi, things like that, and you'd get 0. So that's what that is there. And 0 times 0 is still 0. 0 squared is 0. All right, so now we have what happens when we square the range, and then we have our new range down below. But what happens when we take the negative of it? well, obviously it just flips what all of the values are. So we can kind of just invert what this range is, which I believe it would be from -1 to 0, because if you take 1, it would become -1, and if you take 0, it just stays at 0. So those are the two endpoints, so you can really just go from there. I don't really think you'd have to validate any points in between, but so yeah, just the two endpoints, and then you can end up with your final range, which looks like it is E. Actually, I did not look up the answer before doing this problem, so let me see that it's the right one. 70s E. Okay, sounds good. All right, so yeah, range problems. I think for simpler ones like this, again, we can just kind of graph it out and talk it out to ourselves and figure it out that way. If you'd like the mathematical sort of way of doing it, I think you can kind of do it like domains, where there's certain like restrictions that um, can affect your range in different ways. I'd have to actually brush up on it myself. I don't really remember how to do that, but I'm sure there's some kind of way that they probably taught you in class. But this, I think this was the fastest, easiest way of doing this specific problem. All right, question 8. This problem is weird because it's just testing you on this one trig identity, and just asking you to rearrange this one thing, and it's like I haven't really seen this come up yet. So I'm just going to explain it real quick right now. So the one trig identity that it's testing you on is the Pythagorean identity, which is where sine squared of something plus cosine squared of something of x, or usually it's theta actually, cosine squared of theta equals 1 every time. So any angle that you plug in there, it will equal 1 if you sine squared plus cosine squared. So we're going to use that to rearrange this problem or this expression into one of these. So the way, the weird way that I think it wants you to do it is we're going to set the inside here, so the inverse sine of x. So inverse sine of x, we set it equal to theta, and then we're going to solve for x. So we take the sine of both sides. So x equals sine of theta. Now using that, we can go ahead and plug in a couple different things into the identity in order to get rid of all of the thetas. So we can substitute. So sine squared theta is really just sine of theta squared. In case it looks kind of weird. It looks like you're, I don't know why they put the squared there. I guess it's to differentiate it from sine of theta squared, which is a uh, very different equation. But anyways, we're going to replace the sine theta here with x because x equals sine of theta as we defined. So this is going to become x squared plus cosine squared of theta. This theta here, we're going to replace it with inverse sine of x, which is equal to theta as we said over there. So inverse sine of x equals 1. And hey, we can see now this term here is looking pretty similar to the original problem, cosine of inverse sine of x. We just have this squared here, and of course this other term on the left there. So we're going to do a little rearranging and get this looking back to that. Whatever's on the left side or the right side here is going to be our answer. So if we subtract x squared from both sides, we get cosine squared of inverse sine of x equals 1 minus x squared. And then we can square root both sides. So cosine of inverse sine of x equals the square root of 1 minus x squared. So that is the answer, and A. Um, excuse me. Um, yeah, okay. Yeah, just testing you over that one trig identity. I don't really know why they did that. I mean, it is a pretty popular trig identity, but there's like three other ones. I don't know why they'd, do like all three in one problem, but I digress. I don't think this will come up on a whole lot of these exams. This is a bit different than a lot of the other trig identity problems. But if you do get something like this, just remember the main one, which is this, sine squared plus cosine squared equals 1. and that sometimes you can sort of define, whoa, my entire screen just went black for a second. You can like define your own sort of, uh, I guess, relations between trig like x, theta, and then you can substitute things in, and then eventually you can rearrange your work into the right answer. So that's how I would do it. All right, question 9. This is a limit. So limits, they have a value that x is approaching. And typically with these limit problems, if you were to just plug in the value that x is approaching in for each of these x's, it would end up being like undefined. Like you'd be dividing by 0, or you'd be square rooting a negative number or something weird like that. So let's actually see that here. We'll go ahead and evaluate it. This is 2 times 1 squared minus 1 minus 1. That equals 2 minus 1 minus 1, which equals 0. So yeah, since we're dividing by 0, if we were to plug in 1, we can't just plug in 1. Like if it ended up actually simplifying all through and there's nothing funky about it, then that would be our answer. We'd already be done. But because we're dividing by 0, we need to put in a little more work. So I think the easiest way we can solve this limit is by I think we can rearrange both the top and the bottom, and then after the rearranging, we can cancel out some terms. And then with those canceled out terms, we can plug in 1 into the product of doing that, and then it won't be messed up anymore, and we'll get our answer. So um, in order to rearrange both the top and the bottom, looks like on the top, that is a difference of squares. And you know that with difference of squares, you can break it up into 2 terms. The first one is the square root of the first term plus the square root of the, square root of the first term. So square root of x squared is x, plus the square root of the second term, which is 1. And then the same thing, but the sign is flipped, so x minus 1. So that's the top rearranged. Now the bottom, I think this is, I kind of forget um, the term for it, the word or the phrase that it's called, but we can do the same thing. It'd be the same 2 terms where you'd multiply them out and then it'd get back to what we had down there. So it looks like to get this, it'd be 2x and x there. Since it's ending in a 1, we know that both of these must be 1s. And since it ends in a minus, we know one of them must be a plus and the other might be a minus. We've got 2 cases here. So does this case work? Let's see, the final term would be, no, not the final term. The middle term would be 2x plus, no, minus 2x plus 1x, which equals negative x, and that is the middle term. So yeah, we've got it right right here. 2x plus 1 times x minus 1. That's the bottom now. And we'll see we've got 2 of the same terms now, the x minus 1 term. So we can go ahead, cancel both of those out. We're just left with x plus 1 over 2x plus 1. And now with that, if we were to just plug in 1, it wouldn't be dividing by 0 anymore. So we'll just plug in 1, simplify, and we'll have our answer. So this becomes 1 plus 1 over 2 times 1 plus 1. This is equal to 2 over, say 2 plus 1 is 3, 2/3. So yeah, this was more of a basic limit where you're just asked to rearrange and simplify the limit, and then after doing that, it won't be dividing by 0 anymore. Just know what you learned back in algebra and pre-calc. Difference of squares, splitting up a polynomial into 2 binomials, and that's really all there is to it. And then just simplifying there after that. All right, question 10. We are nearing the end now. Come on, is this thing gonna go away? Usually it just fades out. There we go. All right, just the limit. So evaluate the limit if it exists. Usually they exist. So, all right, so for these limits, first thing I would recommend is just plugging in the value that x approaches. So we're just going to plug in 2 for all the x's here. Most of the time, if not all of the time, we're going to get like a dividing by 0 error or like a square root by a negative number or something like that. So it won't work out most of the time, but we can still just check it nonetheless. So this will become 2 minus 2, which is 0, over the square root of 2 squared is 4, 4 plus 12 is 16, the square root of 16 minus 4, which equals 0 over square root of 16 is 4, 4 minus 4 is 0. So 0 over 0, yeah, that's usually how these go if you just plug in 2 right at the start. But the cool thing is, because we got an indeterminate form, an indeterminate form is either 0 over 0 or infinity over infinity. An indeterminate form means that you can use L'Hopital's rule on this limit. So what L'Hopital's rule means is if you take the derivative of both the top and the bottom, uh, you'll still have basically the same limit. So when you do the derivative of the top and the bottom, and then you can plug in 2 after that, it'll probably work out and you'll get your right answer here. It doesn't change the limit at all. So that's what we're going to do now. We're going to take the derivative of both the top and the bottom. So a derivative of the top, x minus 2, that's certainly the easier one. This just becomes 1 because this is x to the first power. And when we do the power rule, when we move the 1 out to the front, that becomes 1 times x to the 0th, and x to the 0 is just 1. And then a derivative of any constant is just 0, so we can drop it. And now for the bottom, definitely the trickier one because we've got this square root here, which looks intimidating, but just remember that the derivative, no, sorry, just square roots are just the power of 1/2. So this is just x squared plus 12 to the power of 1/2 minus 4. Excuse me, and that makes it clear. Now we can use the power rule here. We can bring the 1/2 out front. So this becomes 1/2 times x squared plus 12 to the power of, so 1/2 minus 1 is negative 1/2. And we're not done at this point yet because I think this is the first time that you may be learning about the chain rule now. So the chain rule is whenever you take the derivative of a term of something, and that something is not just an x like it's anything else. Like so up here when we took the derivative of x, that was just 1x. When we took the derivative of x, we didn't need to do anything else. But now we're taking the derivative of this entire thing here, x squared plus 12. And whenever that happens, you have to multiply the whole thing by the derivative of the inside, which is x squared plus 12. So times the derivative of x squared plus 12, this is 2x. Yeah, just 2x because derivative of 12 is just 0. So there we go. That is a bite-sized chain rule explanation, and then as well as the 4, that gets dropped because derivative of constants is just 0. So there we go. We have our derivative now. We can basically just plug in 2 at this point, but before we do that, I'm going to simplify it just a little bit because I don't even know how I'd take care of this negative 1/2 power if I was just asked to figure out what that is. So I'm going to put that on the top. So what putting on the top means, it means it flips the sign of the exponent. So this now becomes, why is it not erasing? There we go. So this will become x squared plus 12 to the 1/2 power. And remember, 1/2 power, that just means a square root. So this becomes the square root of x squared plus 12 all on the top. I'm going to move this 1/2 out to the top 2 because dividing by a half is the same as multiplying by 2. So the 2 is just on top now. And then all divided by what's remaining, which is the 2x. So there we go. Doing L'Hopital's rule on this original limit gives us this. And now, oh yeah, if we plug in 2 into this, it won't divide by 0 anymore. So we'll probably get our right answer. So plugging in 2, we get 2 times the square root of 2 squared plus 12 all over 2 times 2. Evaluating this becomes 2 times the square root of 16 all over 4. Square root of 16 is 4, so these cancel, and we're just left with 2, which is B. So yeah, a L'Hopital's rule question. I think this was the first one. So yeah, you can do L'Hopital's rule. You can't just do L'Hopital's rule on any limit that you come across. It has to be when that limit is an indeterminate form, aka when you plug in the value and you get 0 over 0 or infinity over infinity. So that's an indeterminate form. You can do L'Hopital's rule on it, which is where you take the derivative of both the top and the bottom, and then the limit won't really change at all. You can still evaluate it and get your right answer. Sometimes you'll have to do multiple L'Hopital's rules, but in this case we didn't have to, so that was good. Question 11. We are getting real close now. Calculate the limit. Another limit. Wow. Okay, so the limit as x approaches -1 from the right side. That's what the plus kind of means there. It means, like in a case where we have, let's say this is just an example function. We have something like this, where the function kind of like makes a big like divergence right there. Normally, the general limit as x approaches this x value, it wouldn't exist. But the limit as x approaches this value from the right side, looks like it approaches -infinity. When x approaches the value from the left side, looks like it approaches positive infinity. So that's what that means. When a limit approaches a value from a given side, it'll either be the left side or the right side. That's what that means. It just means you're looking at that one side instead of both of them. So knowing that, we can tackle this limit now. Um, all right, so again, what I like to do for a lot of these limits is just plug in the value and see what happens. Sometimes it'll work out. Sometimes you'll see you need to do L'Hopital's rule. Other times, which I think like this, you will get infinity. So looks like if we plug in -1, we get -5 on the top and -1 times 0 on the bottom. So we get -5 divided by 0. So in this case, it's not in indeterminate form, but it's also not like a valid answer. Like it's infinity. It's dividing by 0. That's not really allowed. So, but what we can know about this is that the answer will be some form of infinity. It'll either be positive infinity or negative infinity because the denominator is 0. So knowing that, we can already cross off 60% of our answer choices. So if you're like, if you only know the first 10% of this problem, you can already make it a coin flip. Just figure out which, if it's positive or negative infinity. Uh, well, you might actually say right off the bat, well, it looks like it's negative infinity, right? Because it's -5 over 0. Usually 0 is like kind of positive, not really negative. So it'd be negative infinity. But that is, well, it could be the case, but you can't just immediately determine that based on that. How we are going to determine it is using this. So we're going to do a number line here. So we've got a number line now. We're going to make the middle the value that it gave you, -1, and we're going to define 2 points on either side of it. You want to do the closest points that you can do without making it like a super decimally number or fractiony number. Usually whole numbers work. Like we'd probably want to do -2 and 0. Oh, actually, we probably shouldn't do that because what we're going to do is we're going to plug in these two numbers into this. But if we were to plug in 0, we'd get dividing by 0 again. So we probably shouldn't do that. We should do something like -1/2. That's closer to -1. So let's see what happens when we plug in -2 and -1/2 into the limit. So plug in -2, we get -6 divided by -8 times -2 plus 1 is -1. So we get, let's see, we get a negative answer over we get a negative numerator and a positive denominator, so this becomes negative. I'm not even going to figure out what the actual answer is. I just need to know its sign, just its sign, negative or positive. So on the left side, it's going to be negative. And on the right side, I'm guessing it's going to be positive, but let's check just in case. -1/2, when we plug it in, we get on the top, it is going to be still negative. I don't really feel like figuring out that fraction. It's just going to be negative on the numerator, and on the bottom, it's going to be a negative times, let's see, 1 minus 1/2 is +1/2, so it's going to be positive. So on the top, we've got negative. On the bottom, we've got negative. So this is going to be positive because negative divided by negative is going to be positive. So on the right side, we've got positive. The left side, we've got negative. And now, remember what I told you earlier about what the, you know, when you're approaching when you have a limit and x is approaching a value from a given side, you just look at that side. So we're just going to be looking at the right side here. That's what positive means. We're just going to be looking at the right side, and the right side is positive. So our answer is positive infinity. So it looks like at the point -1, at the x value of -1, the function is going to dive into negative infinity at -1 as it approaches -1. So this is -1. And on the right side, it's going to approach positive infinity. It's going to accelerate up to positive infinity. That looks like what this function is kind of doing. So yeah, okay. So figuring out these I guess these line problems or these like approaching from a given side problems. Just remember one of these cases where if you plug in the value and you get a non-zero divided by 0, you should probably use this number line trick where you just fill out those 2 points on either side. Don't even really need to figure out the values, just know their signage, and then you can figure out if the answer is positive or negative infinity. Okay, question 12. Woohoo, this is the last one. I'm tired too. Another limit. This is like the, what, fourth limit on this exam? Maybe fifth? I kind of forget. All right, it's one of those one-sided limits again, where you're just asked to find the limit as x approaches 1 from the right side, just from one side. So that's good to know. Okay, so what I recommend doing for every limit is just plugging in the value that x approaches and seeing what happens. You can usually determine what the best path forward is after you do that. So let's plug in 1 for all these x's. We get 1 minus 1 squared times sine of 1 over 1 minus 1 squared. This will evaluate to 0 times sine of 1 over 0. So, okay, cool. On the right side, it kind of looks like we have to do some work here because on the right side we've got an infinity. We've got a sine of 1 over 0. So that's not a whole lot of fun. Kind of sounds like we need to do some simplifying and rearranging so that we can get an actual value out of this thing. But no, we don't, because look on the left side here. We've just got a times 0 of everything, and anything times 0 is 0. So that is a quick way to do this annoying looking limit. I don't think you have to do any actual work here. I think that's just what it's testing you on, is realizing, oh, this is all just times 0, so the answer is 0. So uh, good way to end this exam, I think. Looking back now, let's see, what was this? If this exam had a tagline, what would it be? I don't know. This was a pretty good exam, actually. Okay, we had a domain problem, which is always on these things. Translations problem. We had it had an inverse, which is good. Properties of logs. Difference quotient. Easy, like a basic. I shouldn't say easy, because like I think this might be your first derivative, but a basic introductory derivative, which is good. A range, properties of, like trig functions, and then just a bunch of limits. So all pretty good problems, I'd say, for what you could expect in an exam, like an exam one, a midterm one. Unfortunately, these midterms are not usually what they seem. It's always like you study 95% of the material, and that last 5% that you didn't study is like all that's on the exam. I feel like that always happens to me. But so that's just, it might happen. You might get some curveballs, but curve will probably save you in those situations. These midterms are usually curved. So yeah, this was a pretty good midterm one. This is, again, this probably, since this is the newest one that I'll be doing, might be the first one that you are watching, the viewer. So I think this was it's a good intro, a good intro to Calc 1.